Bismillahirrahmanirrahim. Assalamu alaikum, students. Today I am with you with another lecture. Today's lecture is about the application of the statistical method, which we have already discussed in the previous lectures. We talked about the idea of partition function, idea of Boltzmann distribution. Now, how to use those ideas to predict the properties of a given system, that is our today's lecture. So we take an example for that. Let me write an example. Let me correct my pen. So we take an example. Which example? We consider an assembly of particles with two states. This is our today's example. An assembly of particles with two states. So let me define this assembly precisely. Let me use the blue color. So consider an assembly of n localized weakly interacting particles adjust my pen. Weakly interacting particles in which there are just two one particle states, two one particle states we label these states by J equal to 0 and J equal to 1 with energies epsilon naught and epsilon 1. It is understood it is under given conditions. So this is our system. So I have an assembly of particles with two states. So N, capital N is the total number of the particles in the system, and we are assuming the particles are localized and they are weakly interacting. And there are just two one particle states available. That means each particle in the assembly has only two states in which it can exist. So we label the states as one state is labeled by j equal to 0 and another state is labeled by j is equal to 1, and these states have energies. Epsilon naught is the energy of j equal to 0 state, and epsilon 1 is the energy of the state j equal to 1. Now, what's our purpose? As I told you, we have talked about the Maxwell Boltzmann distribution function. We talked about that is the thermal equilibrium distribution for a system which is isolated and which is at equilibrium. It is understood. And uh, in establishing that expression, we took the particles which were distinguishable. The same is situation here. We are distinguishing these particles by their locality. So we can use Maxwell Boltzmann distribution and the corresponding ideas of partition function which we have already discussed. Now what we want to use those ideas for this particular system, this assembly of particles with two states, to write down expressions for the properties of the assembly at given temperature T, right? Now, our purpose is, so our purpose is to write down expressions for the properties of the assembly for the properties of this assembly at given temperature T. So this is our aim. We want to write down the expressions for the properties of this assembly of particles with two states, which we have specified at given temperature T, using the ideas we have already discussed. The first thing we want to discuss is the distribution numbers. So let me name it 1. We want to write the expressions for the distribution numbers of this assembly. Let me highlight here. This is our purpose, right? So we discuss first the distribution numbers. So for that, we need to first write the partition function Z. So for this system, the partition function Z has only two terms because there are only two single particle states available in the system. So the partition function Z for the system in question has only two terms, only two terms. Let me write that it is written as Z equal to, let me use another color here. Those of you who are not familiar with the partition function, we have already discussed in the previous lectures. For those people, I will refresh their memory. The partition function Z is summation J exponential of minus epsilon J by kBT, where T is the absolute temperature, Kb is the Boltzmann constant, and Ej is the energy of the state J. So it is the sum for all the states of these Boltzmann factors, as we call them, exponential minus Ej by Kt or Kbt, right? So the system in question has only two states, single particle states, epsilon naught and epsilon 1. So my partition function has two terms. So I can write the partition function for this system as z equal to exponential of minus epsilon by kt plus exponential of minus epsilon 1 by kbt. This is my partition function. Exponential minus epsilon naught by kt is the term corresponding to ground state, J is equal to 0, and exponential minus epsilon 1 by kt corresponds to the term, this term corresponds to the first state, J equal to 1. We can make adjustments in it and we can write it this way. So it can be written as, can be written as z equal to exponential of minus epsilon naught by kt times 1 plus exponential of minus e epsilon by kt. Let me name it first, where epsilon is equal to epsilon 1 minus epsilon naught. So it is what? It is the difference between the energy levels. Energy difference between the levels J is equal to 0 and J is equal to 1. You can check it yourself. You can write it Z equal to exponential of minus epsilon by kt times 1 plus exponential of minus epsilon by kt where epsilon is equal to epsilon 1 minus epsilon naught, which is the energy difference between the two levels which are available to us. One level is J is equal to 0 and second level is J is equal to 1. So this is the equation 1 is the same thing as the previous equation. We have just adjusted it. You can check it. Let me write here, check it. I will change the color. So check it at home. Now this expression for Z, you can note it may be written as the product of two factors. Let me write it. I can write this Z as product of two factors. First factor I call Z of 0 and second factor I call ZTH. That means this factor is my Z of 0 and this factor is Z of TH. See what is Z of 0? Z of 0 is simply epsilon naught, sorry, exponential of minus epsilon naught by kt. This is called 0 point term. This factor, first factor Z of 0 is called 0 point term. Let me name it. Where is my pen? This is my pen. So this factor is called 0 point term. You can see in this Z of 0 point term, it depends only on the ground state energy epsilon naught, because it is exponential of minus epsilon naught by kt. So this Z of 0 depends only on the ground state energy epsilon naught. But Z of pH, which we call as thermal term, we call this as thermal term. This thermal term depends only on the relative energy epsilon between the two levels. You can see from the expression, it contains only epsilon, which is the relative energy between the two levels. So we wrote the partition function, then we split it into two factors. One is Z naught 0 point term, second is thermal term Z of TH. First term depends only on the ground state energy epsilon naught, and the second term, that is the second factor in Z, ZTH thermal term, depends on the relative energy epsilon between the two levels. Now we want to write the expression for the distribution numbers. So let us do that. The thermal equilibrium distribution numbers which are also called as occupation numbers and not, there's the occupation number corresponding to ground state, and N1 occupation number or distribution number corresponding to first state J is equal to 1, may now be written as, may be written as. Before writing them, let me refresh your memory. When we discuss the Boltzmann distribution, that was this expression, and J is equal to N over Z exponential minus epsilon J by ABT. This is the Boltzmann distribution. NJ, this is the occupation number or distribution, equilibrium distribution number for state J at temperature T. So Nj is n by z. Z is the partition function. Capital N is the total number of particles in the system. Then you have exponential minus Ej by kT. Now using this idea, I can use this idea and write the expression for n naught, that is the occupation number or distribution number pertaining to epsilon 0 state, that is the ground state. So let me write. I will use some other color for that. Use black color. So n naught or n0 is n by z exponential of minus epsilon naught by kT. I can put the value of z using equation 1. We have already labeled that equation 1. This one. So it will become like this. It will become n exponential of minus epsilon by kT. Then I will substitute for z using equation first, exponential of minus epsilon naught by kT times 1 plus exponential of minus epsilon by kT, right? So it is simple. N exponential of minus epsilon naught by kT divided by z. I substituted for z from equation first, exponential of minus epsilon naught by kT times 1 plus exponential of minus epsilon by kT. So the first factor in the denominator will cancel with the numerator factor. So you will get this as your expression. So my n naught will become n by 1 plus exponential of minus epsilon by kT. Or I can write it n naught is equal to n over z of pH, thermal thermal term in the partition function, right? N by 1 plus exponential minus epsilon by kT, that is z thermal. So let me name it equation 2a. Let me change the color of my pen. Let me use orange. So I call this as equation 2a, right? Similarly, we can write for N1, occupation number pertaining to first state. It will be N by Z exponential of minus epsilon 1 by kt, right? Then I put the value for Z from equation first. So it will become N exponential of minus epsilon 1 by kt whole divided by Z. So for Z, we substitute from the equation 1 as exponential of minus epsilon naught by kt times 1 plus exponential of minus epsilon by kt. This is the result for N1. N1 is N by Z exponential of minus epsilon 1 by kt. Then we substitute it for Z exponential of minus epsilon naught by kt times 1 plus exponential of minus epsilon by kt. Now I can adjust it. So let me adjust it. Or N1 is equal to N exponential of minus E1 by kt times exponential of epsilon naught by kt let me write clearly divided by 1 plus exponential of minus epsilon by kt. This is my next step. N exponential of minus epsilon 1 by kt times exponential of epsilon naught by kt divided by 1 plus exponential of minus epsilon by kt. It is simple. I have taken a factor in the denominator and taken this factor to the numerator. So its negative power became positive power. So I am here, right? Then I can write it N1 is equal to N times exponential of minus epsilon by kt divided by 1 plus exponential of minus epsilon by kt. Check it. because you know epsilon is the difference in the energy of the two states. It is E1 minus, sorry, epsilon 1 minus epsilon naught. I have used that. So it is n exponential of minus epsilon by kt divided by 1 plus exponential of minus epsilon by kt. Then I can rewrite it this way. Let me use this color. So I can write n1 is equal to n times exponential of minus epsilon by kt over z thermal ZTH. Let me encirculate and name it. So let me first encirculate. I call this 2b. N exponential of minus epsilon by kt, kbt, kb being the Boltzmann constant divided by the thermal is 2b. So we have obtained the expressions for n1, n0, and 2a gives n0, that is the occupation number pertaining to ground state, and n1 gives that is the expression 2b, equation 2b, gives the occupation number or distribution number pertaining to j is equal to 1 state. So we can plot them as function of temperature and understand the behavior. So let me plot them. Let me draw the figure, then I will explain it on this. Let me write it. Here's theta, is 2 theta, and on this axis, we are plotting temperature T. On this side, we are plotting simultaneously my pen. So here I plot n0, comma n1 both. So let me change the color first. Let this be red. And let this line be at n. So here n is representing the total number of particles in the system, that is n0 plus n1, right? I need another line pertaining to temperature equal theta. Let me do it this way. Now, then I find the point where number is half. So here is n by 2. So let me draw a line pertaining to this. So it is not horizontal. Let me clear it. Let me write it neatly. Right? Now let me draw the curves pertaining to N0 and N1 in another color. I will use dark blue for one curve. Let me try to draw it correctly. So it's like this. This curve corresponds to lower state and not lower state. This blue curve is representing the dependence of occupation number pertaining to lower state, ground state, and not with temperature. Let me use another color for the second state. I will use here, I think, purple. It's like this. It goes like this. So this, I will try to make it clear, more neat. It's like this. So this represents my upper state, occupation number pertaining to upper state. G is equal to one state and one. I name it figure 1. My pen, this is my pen. Let me change the color first. I call it figure 1. It is what? It is the dependence of occupation numbers for the two states of this system, which we call SIP in half solid in thermal equilibrium with temperature T, right? Now this theta, we will discuss it. This theta is called the characteristic temperature. First understand the figure. Let me check the figure. This lower state N0, upper state N1, N by 2, N0, N1, then you have temperature T. So let us discuss. So in figure 1, what we have done, we have plotted actually equation 2A and 2B with temperature T. 2A has dependence on temperature T uh, because Z thermal contains temperature. Then similarly, the occupation number pertaining to state 1 and 1 given by 2B has also dependence on absolute temperature T. So we have plotted them. So blue curve gives the dependence of N0 on temperature, and the lower one, purple one, gives the dependence of N1 occupation number pertaining to J is equal to 1 state on temperature. So let us understand some points pertaining to this graph. So you can see that N0 and 1 do not depend at all on the ground state energy epsilon naught. See, N1 doesn't contain epsilon naught. Similarly, N naught doesn't contain epsilon naught. So first point to note, I should write it. So points to note, points to note. First thing I call A, N naught and N1 both do not depend on ground state energy epsilon naught, because epsilon naught is contained in Z naught, and Z naught does not enter to equation 2, right? There is no Z naught in the expressions for N naught and N1, which are equations 2a and 2b. So both the occupation numbers are independent of the ground state energy. This is the first thing. Second thing, let me write second point. N naught and N1, let me write it clearly. N naught and N1 are functions only of, or functions only of epsilon by kt. You can see from the expression, they are functions of only epsilon by kt. Check. N1 contains epsilon by kt, rest is constant, and N naught contains epsilon by kt. This is another point to note. Another thing you need to understand, this epsilon by kt you can think of as a ratio of two energy scales. So you can think of epsilon by kt as ratio of two energy scales. One energy scale is represented by epsilon, which represents the separation between the two energy levels of the particles, epsilon naught and epsilon 1, and is determined by the applied conditions. For example, volume, or in this Sippenhoff solid, it can be determined by the applied magnetic field. So epsilon by kt can be thought of as the ratio of two energy scales. One scale is epsilon, which represents the separation between the two energy levels of the particles, and which is determined by the applied conditions like the volume of the system, or the strength of the applied magnetic field in this case. The second energy scale, which is kt. So this is one energy scale, this is another energy scale. This kt energy scale should be thought of as thermal energy. It is thermal energy, and first one represents the separation between the energy levels. Now this thermal energy kt is determined by the temperature at which the system has attained the equilibrium temperature T, right? Now equivalently, you can write epsilon by kt as the ratio of two temperatures. C. Let me use another color, black. C, I can write this as ratio of theta by T, where theta is epsilon by Kb. Epsilon by Kb is temperature. It has units of temperature. So you can write epsilon by Kt as theta by T, where theta is epsilon by Kb. This epsilon by Kb theta is called characteristic temperature. Because it is this temperature theta is characteristic of the energy level spacing. Characteristic of the energy level spacing, because it contains epsilon, which is the energy separation between the levels. So this temperature theta epsilon by K is the temperature characteristic of the energy level spacing. So you can say this n naught and n1 are functions of epsilon by Kt. You can think of them as the ratio of two energy scales, Kt being the thermal energy scale and epsilon naught the scale of the energy separation between the levels. Or you can think of this ratio as ratio of two temperatures, one theta and another absolute temperature of the system. But the theta temperature is characteristic of the energy level spacing. That means if energy level spacing changes, if you change the external conditions, this theta is going to change, right? Now, another thing from the graph which you need to note, let me write that C. What is that? At low temperatures, mean T is much less than characteristic temperature theta, or that equivalently means Kt is much or very smaller than epsilon C. When T is much less than characteristic temperature, that is we are talking at low temperature situation, or Kt, Kbt is much less than epsilon naught, from equation 2, from equation 2, let me write it neatly, from equation 2, you can see that n naught is equal to n and n1 is equal to 0. I'm saying at low temperature when T is much less than theta, or equivalently Kbt is much less than epsilon naught. From equation 2, if you put these conditions in equation 2 giving the values of n naught and n1, you will get n naught equal to n and n1 equal to 0. These are the expressions for n naught and n1. N naught is 2a, n1 is 2b. You put this condition, low temperature condition, you will get this n naught as n and n1 as 0. That means what? That means all the particles at low temperatures compared to the characteristic temperature of the system, all the particles are frozen out into the lowest energy ground state and no particle is excited into the higher state. I repeat, all the particles exist in the lowest energy ground state and no particle is excited into the higher state. You can see that from the graph also. So we have uh, divided our temperature scale into characteristic temperature. So here I have 1 theta as the temperature, here I have 2 theta and I have 3 theta. So when T is lower compared to theta, you see this N naught is N and this N1 touches the zero. That means at low temperature zone, when theta is very small, I should say, sorry, T, low temperature scale, when the temperature T is small compared to theta, much smaller than theta, N1 is 0 and N2 becomes, sorry, N0 is N and N1 is 0. Let me repeat it. When temperature of the system is low, T is small, compared to characteristic temperature theta, where here in this graph, N1 there is 0, but N0 is N. That in other words means all the particles exist in the ground state. No particle is excited to the higher state, J is equal to 1. This is the observation from the graph, and from mathematical equations, you can obtain this condition, right? So I will give you this as home assignment. Check this at home. Now, another point which I call D, which we need to notice at high temperatures. That is T being much greater than characteristic temperature theta, or equivalently KBT being much greater than the epsilon, we see N naught is equal to N1, both equal to N by 2 from equation 2. So at high temperatures, that means the temperature is much greater than the characteristic temperature, or equivalently KBT is much greater than epsilon naught. What happens? N naught is equal to N1 is equal to N by 2. You can see from the graph. As T is much greater than T, you are in this zone of the graph. This N1 graph and N0 graph both approach to this line where the number of particles is N by 2. That is the meaning. You can obtain this from equation 2. That is your home assignment. I will write it here. Check it. Check this at home. Check this at home. What is the meaning of this? Meaning of this is that at high temperature compared to characteristic temperature, there are equal numbers of particles in the two states which are available. That is, the difference in energy between the states becomes irrelevant. I repeat, at high temperatures compared to characteristic temperature theta, there are equal number of particles in the two states which are available to the system, that is J is equal to 0 and J is equal to 1 state. So the difference in the energy between these states becomes irrelevant for the particles to be in the states, right? I hope this is clear to you. So I stop here. We will discuss another properties of the system in the coming lectures. So before leaving, I will just summarize our results. So what we did today, we considered an assembly of particles with two states. Sometimes we call this assembly as spin half solid. So our system was an assembly of n localized weakly interacting particles in which there were just two one particle states which we labeled j is equal to 0 and j is equal to 1 with energies epsilon naught and epsilon 1. Then we said we will use the thermal equilibrium distribution, that is the Maxwell-Boltzmann distribution, and other related ideas which we discussed previously to express different properties of this assembly at given temperature T. So first we wrote the Z for the system, that is the partition function. We saw it has only two terms, one term pertaining to ground state, another one to j is equal to 1 state, that is the first state or upper state. Then we said that this Z can be written as a product of two factors. One factor is 0 point term, which doesn't contain, which contains the ground state energy, and thermal contains the energy difference between the states. Then we wrote the expressions for using Maxwell distribution function, which we already discussed, Boltzmann distribution function. We wrote n naught and n1, then we plotted them with temperature, and we defined a temperature theta called characteristic temperature, which is characteristic of the energy difference between the states, and we obtained certain inferences, conclusions. First was that n naught and n1 both are independent of the ground state energy. They do not depend. They depend only on epsilon by kT, ratio of two energy scales, or we can think of ratio of two temperatures. One is the characteristic temperature theta. So we saw that at low temperatures compared to the characteristic temperature, all the particles are in ground state. No particle goes to the upper state. At high temperatures, compared to the characteristic temperature, then what happens that particles are equally distributed between the states. For them, the energy difference between the states becomes irrelevant. So this is all for today. I hope it is clear to you. So do not forget to like, share, and subscribe my channel. If you have any queries, you can comment in the comment box. I will try to resolve those queries. Thanks for listening. Assalamu alaikum. God bless you.